reliability and diagnosis. So, well, this you can also read from the title of my talk, which I include our slogan, Arch, know what your machine doesn't know. You will know more about it, so don't worry if you don't get it. So I believe most of us here knows that machine learning systems, right, despite the impressive performance, they can still easily fail and generate errors that we don't expect. And we've heard about all these horrible stories of machine learning failures, especially in high stakes domains such as health, transport, finance, and etc. And those machine learning failures are also a big problem in digital services, which today are largely, supported by AI technologies on one hand, and also generating a profound impact on the society, for example, shaping the public's opinion, right? So we've heard also about this story of Ty from Microsoft that, it's a chatbot Microsoft deployed on Twitter, and it learned to be a racist within just several hours. So we need to build machine learning systems that are reliable, which in many cases also means machine learning systems that are safe, fair, and trustworthy. Now, from technological perspective, the question that we ask here is, what do we need to build a machine learning, reliable machine learning system? Well, to see that, let's first take a look at the machine learning life cycle, a typical one, and to see what we're missing here. So a machine learning life cycle generally involves two steps and two types of stakeholders, and the developers on one hand, and then the users on the other hand who use the system, right? This is, of course, very much simplified. We have many other different types of stakeholders as well. Here, I just show these two types of stakeholders for illustration purpose. So the problem now with this type of life cycle and stakeholders is that, when the system fails, users wouldn't. Well, first of all, they cannot really predict, right? The users, both the users and developers, you wouldn't be able to predict when it will fail. And when it fails, users might be able to provide the feedback to the developers, but then the developer wouldn't know why it occurs and what to do with it, right? So what we're currently missing is a method or tool that can allow us to know when and why a system would fail. And this is exactly the reason why we developed Arch, a diagnosis tool that can help us identify the causes of machine learning failures. And this kind of tool is essential to build any type of reliable systems, being them software or hardware. Right? We cannot really build a reliable system in one shot, but it's more an incremental process that involves a lot of testing, debugging, right, communications between the users, the developers, and other stakeholders as well. So having such a tool is essential to close the loop, and allows for such incremental improvement of the system. I have been mainly talking about the importance from the developer's perspective, but from a broader perspective of different types of stakeholders involved in the machine learning lifecycle, being able to identify the nature of the failures is actually also important. For example, for users, they need to decide when or whether or not to trust the system output, right? And then a tool that allows them to see when and why the system can go wrong is super important for them to determine the trust. And of course, if later on we have auditors as well, and this kind of tool would be super useful for auditors to assess the risks of the machine learning systems. Now, let me give a rough idea of what Arch does. Here, let's consider a scene recognition task where the goal is to classify the images into different indoor rooms, for example, living room, a bedroom, kitchens, etc. So here I show you a hypothetical scenario where the model correctly classifies a living room in the test data, but then fails on the serving data. So test data are the data that we use in the development phase, and serving data are the data that the model encounters after it's deployed, right? So a reason here is for the for the failure in the serving data is that, well, the model should have recognized both, the television and couch being the necessary concept that it should identify, and in recognizing living room, it misses the concept of the couch, right? Which doesn't really matter in the test data because the model can still do it right for the living room, but then it can lead to wrong output in the survey data, right? So this is a scenario that I showed to illustrate, for what reason a model can go wrong. And then what Arch does here is to tell us why exactly the model gives wrong prediction. For example, in this case, it's because, well, in the prediction of the living room, the model, well, fails to recognize the couch that can, well, later on lead to errors in the predictions in the survey data, right? So Arch gives an analysis of this kind of errors, and it also gives us, well, some indication of how severe the problem is by showing, okay, to how frequently this kind of errors can appear. For example, here we show that, the model can fail to identify the couch in 80% of the living room images. And so just to give us some idea about how often this model can fail like this. And on the, at the bottom, I show you, well, some ideas about how Arch is built, right? You can see that, well, the key idea here is to involve human knowledge to describe, on one hand, how the model behaves, and on the other hand, what the model should have learned to behave correctly, right? I'm going to skip this part, and then later on I will talk about it in more detail. So in the following, what I'm going to present is, well, first of all, the key ideas, the technological choices that we made in building Arch. So how do we build Arch? And then I'm going to very briefly talk about where Arch is developed and tested, right, where it's applied. And later on, I will go into introduce some details about individual components in Arch and the entire structure, architecture of the Arch system. So now let me start by explaining, well, how we build Arch, right? And before that, I want to use one slide to explain what we chose not to do. So one way of building high-performance machine learning models, which is the way that we usually do in practice, is that we want to collect, well, as much data as possible with the hope that the machine will behave reliably in application, right? And it turns out that this is not a good solution. We have seen that even those huge models like GPT-3 trained on hundreds of billions of words, or models trained on ImageNet, right? So for both the language and vision cases, those huge models trained on huge amount of data, they can still fail. And they fail, well, actually very easily. So instead of collecting more data, ideally we should instead know, right, what kind of scenario the system would encounter in application, and have those scenarios covered in the training phase, right? The problem here is, of course, that we cannot possibly foresee all application scenarios. Otherwise, we wouldn't, well, need a machine learning system, right? But what we can do here is that, and this is also the main scientific proposition of Arch. So what we can do here is that for anything that we know that the machine learning system should know, we should be able to know what it really knows and what it doesn't know. So this is a long sentence, but it should be easy to get. So the whole idea here is that, well, there is a lot of knowledge that we humans rely on in performing a task that is not necessarily known already by the machine. And currently, we do not have a way yet to know what the machine doesn't know, right? From a human perspective, that the model should know. So there is actually a lot of space that we, if we take the angle of human knowledge, a lot of things we can check, okay, well, to what extent the model is capable of performing a certain task, right? So this is the main idea of Arch. Once we know what the model doesn't know, we can, well, not only fix errors, when those errors are observed, but also potentially reduce errors that are foreseeable before it occurs. And, and for seeing such errors, of course, we need to rely again on human knowledge, right? So this is the whole idea of Arch. And based on this idea, Arch is built with three main pillars. First of all, in order to know what a machine learning knows, right, we need to explain human understandable language, what the model is doing, how it works, right? And this is essentially a machine learning interpretation or explainable AI task. And on the other hand, we also need to elicit domain knowledge from relevant people, for example, domain experts, right, in order to know what the machine learning should know internally. Here, I do want to emphasize the fact that we want to, really describe the entire working logic in order to perform a task successfully. Things that the model should have internalized in performing the task in order to perform the task successfully. So these domain knowledge that the model should have learned internally. And then given what the model really knows and what should know, we can then reason about, right, what are the knowledge that the model should have learned but has not learned. So to know what the model doesn't know, right? So very simple idea. So next, I'm going to very briefly describe some work that we did for each of those pillars before we really dive deeper, right, into individual components of Arch. So for the first pillar, machine learning interpretation, we recently introduced a method that involves humans in the loop to explain what the model has learned. So as I mentioned, right, the key idea of interpreting machine learning behaviors is being able to allow the machine speak in human language, right? What is the knowledge it has learned, how it works. So, but then most of the existing methods, they cannot really describe, machine behaviors in human language, but rather, through saliency maps and etc. So in this work, we involve humans in the loop to attach the semantic concepts to the machine provided explanation of what are the things that it has learned, right? So and this is a key idea here. And this work we first introduced in the web conference last year, and this year we did some more work on the interfaces to explore how well it can support identification of bugs in the debugging of computer vision models. I'm going to introduce this more in detail later. But now, for the second pillar, eliciting requirements, right? Here, the goal is to, involve relevant people to tell us what the model should have learned, right? And there are several problems here that we need to address. First is that, we needed to engage those domain experts, which are, very scarce resource for us, because they are not easily available. So to make it fun, we developed games with a purpose that engage domain experts to contribute the knowledge while playing some games, right? So if you're interested, we have recently introduced this work at the web conference, which also won a Best Paper Award nomination. You can find more about this if you want. I will also give a little bit more introduction to this work later. And then the other problem that we address here is that, we also need a language, right, to allow domain experts to specify the requirement of what is the knowledge the model should have learned, right, on one hand. On the other hand, this language should be able to be easily processable by the machine, so that later on we can compare, right, what the model should know to what it really knows in order to know what the model doesn't know, right? So we are developing a language for these purposes, for requirement specification and for machine reasoning. Now, for machine reasoning, as I mentioned, right, once we have obtained the description of model behavior and what the model should know, specification, we can then reason from these two types of knowledge, the knowledge of what the model doesn't know, right? This essentially is a specific type of reasoning that we call abductive reasoning. inferring inferring from observations to explanations, right? So on the slide, I show you a project that we're currently working on with the Freiburg Hospital in Switzerland, my former colleagues, in the context of prostate cancer detection. We will apply the same idea, right? We have developed already a machine learning model for automatic cancer detection. Of course, it's not perfect. So we engage those doctors, radiologists to give us requirements about what the model should know. And then on the other hand, we ask them, and also involving medical students and even laymen to describe, right, after some training, to describe what model has learned, have seen in the image, right? So we combine these two types of knowledge about what model should have learned and what the model really has learned, right? To infer about things, concepts and logics that model have not learned or have learned incorrectly, in order to know where the model could go wrong, right? This is an ongoing project that we are now working with, and just to use it as an illustration of things that we did here. But we actually are developing Arch in many other different contexts as well. So here I wanted to give a brief idea of the specific applications that we are now currently looking at. So you can see on this slide that some other slides that I copied from my other slide decks. So you, on the top left, you can see an example of application of detecting the compliance of those vehicles and shapes, actually also including shapes that are coming to the Netherlands, right? So in the Netherlands, there is this data science team in the Ministry of Water and Infrastructure Management, and they are teaming up with inspectors to detect the compliance of vehicles. And we are working together with them to build a human AI team to use machine learning to help, right, the inspectors in performing the tasks. And here you can imagine that it's quite important to, well, in order to build a good human AI team, right, it's important that the AI system can tell what are the knowledge that it has learned in performing a specific task, or what is knowledge that it has not learned, right, in a collaboration with these inspectors, so that they can work together to improve the work efficiency, effectiveness. So this is one example. In the middle, I'm showing you here. I'm showing you an example that another example application that we are now currently working together with the National Library of the Netherlands. So basically, the whole idea here is that there are a huge amount of text published every day for different purpose. For example, the government is publish announcement and a lot of announcements about coronaviruses. For example, the measures that they take, suggestions about taking vaccinations, right? So all these publications that might be difficult for the citizens to understand easily. For example, you can imagine, right, all those long text about, okay, what are the measures are being taken to battle against the corona. So there is a big barrier for the citizens to get access, to understand such information. And for that reason, all these municipalities, they have the internal teams trying to simplify this text, right, before it gets published. And then what we're now currently doing with National Library is to develop a tool that can automatically simplify those texts. But of course, again, this is not AI methods. They are not perfect, right? We need to work together with humans, with those domain experts. But again, once we consider this scenario, again, the model needs somehow to be able to explain how it does its work, right? So that the human experts can safely rely on the output of the machine and decide if it's not reliable and decide not to use, right, those machine output. So this is another example. And this slide that I'm not showing here is actually an effort that we are now teaming up with a couple of companies in the context of MVO Robust, which is a national initiative on, well, making AI systems more robust. So what we are now doing here is to work with these knowledge engineering companies and the companies that use those knowledge, for example, ontologies, right, for downstream tasks. And specifically, we are collaborating with some food and nutrition companies to help them create a pipeline that can allow for more reliable creation of the ontologies in the food and nutrition domain. And here again, we consider a human AI collaborative approach, right, in order to create such knowledge reliably and also efficiently. We need somehow to involve both the domain experts and some AI systems, right? And again, it becomes very important that the two parties can work smoothly together. And for that, we need the AI system to tell what it knows and what it doesn't know, right? There are many other applications that I can talk more about, but I think I'm going to skip this slide for the moment before I run out of time. So we're also working with some banks and well, some knowledge institute in the context of urban management. So if you're interested to know more, just get in touch. Okay, now, how much time do I get? I think I might already be running out of time, right?
Yes. So
okay, cool. That's fine. Then I will simply introduce the architecture of Arch and before the question and answering part. So on this slide, I show you. Actually, there's a picture that I made last night. I show you the architecture of Arch. You can actually see it from different angles, right? So horizontally, it's different. There are different layers of Arch, where the top layer is the interface part, including, right, first of all, the interface part that that interacts with the different types of people involved, right? Essentially, Arch is a human-in-the-loop tool, right? So there are different types of people that need to be involved. And then there are, in the middle, there are some components that implement some of the functions that I talked about earlier, including, well, explaining machine behavior, eliciting requirements from domain experts, right? But here I also show, I want to emphasize that we also consider the data part as well. Up until now, I was mainly describing Arch from the model perspective, right? Understanding what model is doing, what it should be doing. But in order to really start the analysis, we needed to inject some data into the model, right? Some data into the model so that we can start analyzing when things can go wrong. And it would be best if this data is already some data instances that are hard, that are difficult and hard for the machine to get it right. Right? So we need to have another component that can help us collect the difficult cases. And what makes a data instance difficult? Well, we need, again, here rely on human, different types of stakeholders. This is the main idea, right? We need to leverage human perspectives of what are the things that are difficult for the machine to handle. And this is the data part. And once we have that, right? Once we have that, we can start analyzing what's going on in the model, what are the things that model should have learned, right? And that's the reasoning we can get what the model doesn't know, right? And of course, in the middle, we have also this scheduling part because there are different workflows involved. Some of them interact with each other, right? So in order to guarantee that we can get the correct result on one hand, but also in a cost-effective manner, right? We need to somehow to, cleverly schedule those different workflows. Yeah, thanks all. This is a very brief introduction to our work in Arch. Now let me maybe simply give me a second. Let me jump to the last slide. And again, there are a lot of other, as I was saying, right? So up until now, we have just introduced the explanation and requirement elicitation part. There are many other components that I haven't really introduced in very detail. So in order to get to know more, please get in touch. And we are the Kappa team at the Web Information Systems Group at TU Delft, a very young team that is now, starting to do some, I believe, really exciting work on understanding machine learning models, how it works, when it would fail, right, and whether or not it aligns with our expectations. So get in touch if you're interested. Thanks.
Thank you, Jay, for the excellent talk. Now we are in the Q&A session. Are there any questions? So maybe I can start with one simple question. Jay, so as you can see today in the keynote, Dr. Guo mentioned sometimes the machine learning model simply doesn't work for the specific use case, or it is possible that the presentation is not right. So I want to ask, for your approach, or let's say in a high level, what types of errors there could be in a machine learning model? And today, Paul also mentioned the word of debugging. So I also want to know what's the difference between their debugging and your debugging of errors.
Thanks, Rihan. Very good question. Questions that I've also been wondering about all the time. So first of all, maybe let me first respond to the second question. What is the difference between the debugging that Paul was talking about and the debugging that we are now looking at, right? So I think Paul mainly take data perspective, trying to find, okay, what are the things that could have gone wrong in the data pipeline. And so, for example, the lack of certain data points, some data labels, for example, not being clean enough. What we are now doing here is more on the model side, because getting the data is one of the steps, right? And afterwards, we need to train the model before applying it in real use cases, and a lot of the cases, the feedback about the errors that we might get from the use case, right? It might be fed back to the, it might not be easily find out in the original training data. Sometimes we need to know what's going on in the model to see what exactly things go wrong. So basically, we need to know the entire model of how the model uses this data, right, and convert that into task-specific knowledge in performing a certain task. So here we are looking more at the model part in this sense. Your first question being,
like,
sorry,
what types of error there could be?
Oh, yeah.
What the reason why the machine learning model went wrong?
So depending on the angles that we take, I can have different. We can have different discussions about this question, right? In the talk, I was mainly categorizing the errors into two different types. One is the errors that we can get during the development phase, and in that case, the errors that we are dealing with is mainly the errors that we can observe, and also that the errors that we can guess, right? We can guess that model might happen. So these are the cases for the that I use to describe the debugging into these two different types, reactive and proactive, right? The cases when we observe an error and the cases that we need to, even we do not observe, we might be able to identify by opening the model up, right? And also by comparing what the model learns to the knowledge that domain experts would specify. So reactive and proactive is actually the same case that these different types of errors we might deal with more as well in the deployment phase after the model is start to be used in practice. But there we might be mainly dealing with the errors in a reactive way. So this is one angle, right? Depending on when the errors might occur and whether or not we can observe such errors. but in terms of the real content about these errors, right? So what are the different types? So here, what I've been mainly emphasizing in our project is that we need to deal with this type of errors of, that by comparing model norms to human norms, these errors that we can find. So it somehow still is limited by the capability of humans on one hand, right? But you can see actually one specific type of errors that we can deal with here, but might not be able to be dealt with in any other debugging method. Other cases when the error occurs when the data distribution is very different from the data distribution that we see in the training part. So there are these methods, well, adversarial training or learning, right, where we try to identify the data instances that are, well, following similar distribution as the training data, and then by automatically identifying or generating these data instances, we can somehow identify to some extent, right, when the model might go wrong. But this is again is very much limited to the existing data distributions. Because all these adversarial learning methods, they follow the original data distribution that is given in the training phase, right? But in our method, because we leverage human understanding of how the task might look like, how the data might look differently, right? The data can be very different from what we observe in the training case, and this can, I believe, largely expand our ability to identify potential errors that model might produce in the real applications.
Thank you very much.